Sorry for the interruption in the internet connection. So I have to restart the connection and start the class as well. So where we are, atomic number and mass number. The atomic number of an element is equal to the number of protons in its nucleus, which also determines the identity. The mass number of an element is the sum of its protons and neutrons. Moving next, electrons distribution means electrons occupies regions of space around the nucleus known as orbitals. These orbitals are characterized by specific quantum numbers that describe their energy, shape, and orientation in space. So, moving, this is how the electrons distributions are categorized. And next, moving to quantum numbers. Each electron in an atom is described by a unique set of quantum numbers. There are principal quantum numbers, which denote as n, indicates the main energy level cells of the electrons. It determines the distance of an orbital from the nucleus and takes integer value starting from 1. Next is azimuthal quantum number, which is denoted by 1. Determines the shape of the orbital and takes values from 0 to n minus 1. The values of 1 correspond to different types of orbitals. That is, S into 1 equal to 0, P 1 equal to 1, D is 1 equal to 2, and F 1 equal to 3. Magnetic quantum number denoted as ML. Specify the orientation of the orbital in space and takes integer value from -1 to +1. Spin quantum number, which is denoted as MS, describe the spin of the electrons within the orbital and can have value of plus half spin up or minus half spin down. So this is the spin quantum number. And next is Aufbau principle. Aufbau principle, this principle states that electron filled with atomic orbitals starting from the lowest energy level, that is n equal to 1, and proceed to higher energy level in order of increasing energy within a given energy level. Orbitals with lower values of 1 are filled first, followed by higher values of 1. Next is Pauli's exclusion principle. These are the basic principles which you have to remember for the examination purpose and for your class knowledge. According to this principle, Pauli's exclusion principle, no two electrons in an atom can have the same set of quantum numbers. This means that its orbital can hold a maximum of 2 electrons with opposite spin up and spin down. Hund's rule. Hund's rule is when filling degenerate orbitals with the same energy level. Degenerate orbital means orbitals with the same energy level. Electrons will occupy empty orbitals singly with parallel spin. When you have a parallel spin before pairing up, that is called Hund's rule. This minimizes electron repulsion and stabilize the atom. Electron configuration. The arrangement of electrons in an atom is described by its electron configuration. We specify the distribution of electrons among the various orbitals. Electron configuration can be represented using the notation of the periodic table or by using orbital diagram. So this is the end of our first unit. Now moving to There are several questions given, quiz exercise, question and answer given in your exercise of SLM. So please go through it and read thoroughly to understand better. And now moving to our Unit 2. Unit 2 is topic is semiconductor electrical properties. This is what we read. These are the basic of physics, electrical subject, which is required for the better for a career purpose as well as for your better understanding in the electronics. If you want to go for the electrical field, then you get it is important to study about this subject. So electrical properties, semiconductor, generation and recombination of charges, concept of carrier concentration will be knowing in this unit. Let's have a basic introduction on electrical properties of semiconductor. The electrical properties of a semiconductor encompasses several key characteristics that define its behavior in electronic devices. That is conductivity. Conductivity is the immediate conductivity compared to insulator and conductor. The conductivity of a semiconductor can be modified by doping, temperature, and applied voltage. So, which, for example, in a fridge stabilizer, now where we can set the temperature based. Next is carrier concentration. Carrier concentration terms semiconductor contain charge carriers, electrons and holes that contribute to conductivity. The concentration of these carriers determines the material's electrical behavior and can be altered through doping or temperature change. Next come mobility. Mobility refers to the ease with which charge carriers move through the semiconductor material in response to an electric field. High carrier mobility is desirable for efficient device operation. Next is high carrier mobility. Next is energy band structure. This is semiconductor having characteristic energy band structure consisting of valence and conduction band separated by a band gap. The band gap dictates the energy required for charge carries to transition from the valence band to the conduction band, influencing conductivity and optical properties. Next, doping. What is doping? Doping involves intentionally introducing impurities into a semiconductor to alter its electrical properties. Adding donor or acceptor atoms can increase carrier concentration and conductivity, enabling the customization of semiconductor material for specific application. Next, temperature dependence. What is temperature dependence in electrical? The electrical properties of semiconductor are strongly influenced by temperature. Change due to thermal generation or recombination process. Understanding and controlling these electrical properties are essential for designing and optimizing semiconductor devices such as what? Transistor, diodes, solar cell, and sensor. Okay. Next, moving to our next topic, this one section, generation and recombination of charges. These are the few generations and recombination of charges. One, starting generation of charges. Here you see this. I will highlight. So, generation of charges. Here you see, generation refers to the creation of electrons hole pair with within a semiconductor. Okay, this can happen through various mechanisms, including so generation of charges comes with many other recombination like absorption of photons. When photons with sufficient energy are absorbed by the semiconductor material, they can create electrons hole paired through the photoelectric effect, like photograph, like camera, for example. And thermal energy is at finite temperature. Thermal energy can provide sufficient energy to break covalent bonds in the semiconductor, creating electrons hole pair. Okay. Next is impact ionization. High energy carriers, such as those generated by electric field or by the injection of carriers, can collide with atoms in the semiconductor lattice, creating additional electrons hole pair. Next is recombination of charges. Recombination of charges occurs when free electrons and holes combine, okay, leading to the neutralization of charge carriers. There are several types of recombination. One is direct recombination, trap assisted recombination, auger recombination. These are the three types of recombination which we have for this unit. So first is direct recombination, means when electrons and holes combine directly. Then it's called direct recombination. Trap assisted recombination is charge carriers can become trapped at defect or impurities in the semiconductor lattices. Then it's called trap assisted recombination. Auger recombination is a free carrier recombines with another carrier, transferring its excess energy to a third carrier, which then gains enough energy to cause additional carrier generation or recombination. Next, concept of concentration. Carrier concentration is crucial concept in semiconductor physics. This is called semiconductor. It's a chapter in semiconductor physics, referring to the density of charge carriers within a semiconductor material. Charge carriers in semiconductor are electrons. That is negative charge. Electrons are negative charge. Holes is protons. That is positive charge, which contribute to the electrical conductivity of the material. There are two main types of carrier concentration. One is electron concentration, that is denoted as with N. This represents the number of free electron per unit volume in the semiconductor materials. Next is hole concentration. One is electron, one is hole. Hole concentration is denoted by P. This indicates the number of holes absent of electrons, okay, per unit volume in the semiconductor. Holes concentration is denoted by the symbol P and is also expressed in the unit of carrier per cubic centimeter, that is cm to the power minus 3. That is the formula. Not formula, it's express of unit. So this is the end of our second unit. Now moving to our third unit. You can go through your SLN and study, go through with different questions, essay questions will be there, multiple choice question will be there. So you practice for better understanding. Next, moving to our third unit. that is semiconductor basic energy band. So here we'll learn about energy band theory of crystal, insulator, semiconductor and metals, uh, mobility and conductivity, types of semiconductor. Moving to our introduction part, energy band theory of crystal. That is, what is energy band theory of crystal? It's a fundamental concept in solid state physics, particularly in understanding the behavior of semiconductor. It describes the arrangement of energy level within a crystalline solid, which determine its electrical conductivity property. Introduction to energy band. So we move to our introduction to energy band. It is a crystal lattice. Electrons are confined to specific energy level due to the interaction between atoms. These energy levels form bands of allowed electrons state, separated by energy gap. Then valence band. Valence band is the lowest energy band called the valence band, is occupied by electrons in their ground state. That is ground state, that is crystal lattice. Introduction to energy band is that in crystal lattice, electrons are confined to specific energy level due to the interaction between atoms. But in valence band, what happens? Occupied by electrons in their ground state. Okay, these electrons are tightly bound to their respective atoms. Now next, conduction band. Conduction band is above the valence band. That lies the conduction band, which contains empty or partially filled energy state. Electrons in the conduction bands are free to move throughout the crystal and contribute to electrical conduction. Okay. Next is energy gap. Energy gap is band. It's also known as band gap. The energy gap between the valence and the conduction band is crucial in determining the electrical properties of the material. In conductor, this gap is effectively zero. Okay, allowing electrons to move freely between bands. In insulators, the gap is large and electrons are required. Significant energy to transition from the valence to the conduction band. Okay. Next is Fermi level. What is Fermi level? The Fermi level represents the highest energy level occupied by electrons at absolute zero temperature. Next, doping and carrier concentration. Doping introduces impurities into the crystal lattice, okay, altering its electrical properties. And next is effect of temperature. How it affects the temperature? Increasing temperature leads to thermal excitation of electrons into the conduction band and increasing conductivity. However, excessive thermal energy can also break covalent bond, leading to intrinsic carrier generation and reduced conductivity. Next is band structure calculation. How it's calculated? The energy band structure of a crystal can be calculated using quantum mechanical model, such as the tight binding approximation or density functional theory. This calculation provides insight into the material electronic properties and are crucial in designing semiconductor devices. Okay, go through with the others type of mobility and electrical conductivity and all. Now types of semiconductor. If we move forward with these types of semiconductor, there are intrinsic semiconductor, extrinsic semiconductor, n-type semiconductor, p-type semiconductor, compound semiconductor, and organic semiconductor. How many it is? 1, 2, 3, 4, 5 and 6 semiconductor. There are 6 types of semiconductor. Now let's see one by one. Intrinsic semiconductor are pure semiconductor material. Okay, with no intentional doping. Example includes pure silicon, this is Si, and germanium, that is Ge. Extrinsic semiconductor are doped semiconductor material where impurities are intentionally added to modify their electrical properties. Okay. Next is N-type semiconductor. It's a dope with elements that provide additional free electrons, such as phosphorus, P, or arsenic, As. These impurities are known as donor, and the resulting semiconductor is called an N-type semiconductor. Now, P-type semiconductor is doped with elements that create holes, that is, positive charge carriers, such as boron, B, or gallium, Ga. These impurities are known as acceptors, and the resulting semiconductor in is called a p-type semiconductor. Compound semiconductor. Compound semiconductor are composed of two or more elements from different groups in the periodic table. These materials often have superior electrical and optical properties compared to the elemental semiconductor. Example: gallium arsenide, this GaAs; indium phosphide, this INP; gallium nitride, this GAN. And next is our organic semiconductor. Organic semiconductor are made of organic, this is carbon-based molecule or polymer. They are lightweight, flexible, and can be processed at lower temperature compared to inorganic semiconductor. Okay. So this is the end of our unit 3. So we'll stop our class till here. You go through it and study thoroughly to understand from your side. Don't depend only in the class. So thank you. See you in the next class. We'll start in the next class from block 1 unit 4. Okay, since we have only 1 hour, so we will stop here. I don't want to make the class boring. Thank you.